All right, so Unit 5 is all about the concepts of exponential functions and something brand new to us called a logarithmic function. Today, we are going to jump in and start learning about an exponential function, what one is, and what its graph looks like. And what I have right here for our do now is a little equation that would be an example of an exponential function. We know something is exponential if our input variable of x is actually in the exponents. So I wrote that down as a vocab thing for you guys later, but just realize that something is exponential if your variable x that you plug in for is up in your exponents. It's a new type of graph, which means now we're going to have, of course, new rules and try to figure out a pattern for what our picture is going to look like. So, our first job, and you guys should be pretty used to this by now, but we're going to go ahead and make a table to figure out what x's and what y's we want to actually graph. If we're really not sure what to do, like where to look, etc., you can't go wrong with doing the numbers -2 to +2. So I'm going to start there. I'm actually going to start in the middle here and come back to the negatives. If I plug in a 0 for that x right there, what I would end up having is I would have 5 to the 0 power, which we all know is equal to 1. Anything to the 0 power equals 1. So I would go ahead on my graph. Actually, I'm going to hold off on my graph, but I would put a dot at 0, 1. My next point, if I plug in a 1, 5 to the first power is a 5. And if I plug in a 2, 5 to the second power is a 25. Let's go over here now and plug in the negative entries. If I do 5 to the negative first power, we already know this is going to send my 5 to the bottom of the fraction, and I'm going to get 1 over 5. 1 over 5 is a 0.2. And if I do 5 to the negative second power, that's going to get me 1 over 5 squared, or 1 over 25, which is like 0.04. And what I could do is if I wanted an even better picture, I could plug in even more x's, -3, -4, etc., 3, 4, 5. And I'm going to do at least one more point right here and plug in a 3, just to show you guys what ends up happening. If I plug in a 3 for x, 5 to the third power is going to get me 125. And if I wanted to go one more and plug in a 4, I would get out a 625. Exponential equations grow so much faster than any other type of graph we will talk about in Algebra 2, and it's not even close. They get out of hand really, really quickly. So when we do our tick marks in exponential graphs, we generally have to go by something, scale it kind of big, because our numbers do get out of control pretty fast. I'm going to use these dots right here and get my graph going. And because my biggest number is 125, I think what I'm going to do here is, and there's not really a right answer per se, but I think what I'll do is I am actually going to go by tens, even though I'll be a little bit off the picture. I could go by something like 25s, but I'll go by tens. So my first tick mark right here is going to be a 10, and then I'd be at a 20. But on the x-axis, I'm just going to go by ones. The x-axis will be totally normal. I'm going to pause and throw that up so you guys don't have to watch me graph points, and we'll talk about it. All right, so I've got some dots on my little picture right here. Now I want to comment on a couple things. If you look at all of these y values at the very beginning right here, like if my tick marks go by 10, how am I ever going to fit a 0.04? It just is so minimal, like compared to this 10 right here. Now it's not going to go negative, but it's going to get so close to 0 that it almost looks like a 0 right here. And the same thing with these first couple points, you can barely even distinguish where they're at. Then I had 2, 25, and my next point got out of hand. It was 3, 125. I'm already off the picture. If I did just one more dot here, and I did 4, I would need to climb on a ladder to get up to 625. It wouldn't even fit on what you guys can see right here. So exponential graphs have two kind of different sides to them. You have on this picture, the right side of this picture, which I'll try to draw right here. And one side of an exponential, once it gets going, is just so incredibly steep. It shouldn't be entirely vertical, and it's hard for me to draw perfectly with my little tablet here. But this line isn't completely vertical. It still angles to the right a little bit, because like I said, you can get to 4 and 5 and 6, but it just grows so crazy fast. The other side of my exponential equation goes really, really, really flat, like this. And again, not super great. I missed my dots right here, but you have a really steep side and you have a really, really flat side right here. This flat side of the picture has a weird kind of fancy name. So I'm going to draw a little dashed flat line right here at 0. It turns out this exponential graph will never, ever, ever dip below 0. Think about like if I plugged in, for example, I don't know, a negative 50. Say my x value was negative 50. Well, that would mean I would have to do 5 to the power of negative 50. Well, that's 1 over 5 to the 50th. And that's a really, really absurdly large number right here. 1 divided by giant number still doesn't make 0, but my calculator is eventually just going to give up and round it to a 0. This concept right here of going flat at a number, but not actually reaching the number, because we're never actually going to equal a 0, it just basically rounds to 0. It is called a horizontal asymptote, which is a really strange vocab word here. Horizontal, asymptote. And what a horizontal asymptote is it's a place where your graph levels out and goes flat. It doesn't actually, in this situation, ever equal 0, but the horizontal asymptote for this picture would occur at the value y equals 0. I want to pull up my calculator here and show you guys how this looks on your graphing calculators. So if I was going to go into the y equals, I would type for my equation 5 to the power of x. And if I hit graph, you're going to see a nicer looking picture than what I actually do right here. And you can see this steep part is matching up with what you see right here. However, my picture only goes up to the tick mark of 10 right there. So like if you look, I can't even fit the value that you guys were seeing. I got 2 comma, and I'm already off the picture right here at like 21. So it's all about the scaling that you use. Now it looks to me on this picture, the calculators don't do a very good job with graphing asymptotes in general, for whatever reason. At least my older one doesn't. So if you keep going right here, the graph does continue. It basically just blends in right here with my axis. And if you look at what happens to the y value as I go left, I'm only at negative 3.8. It's already so close to being 0. This is scientific notation, move the decimal 4 spots. And if I just keep on cruising right here, I'll go to the table to make it easier to see. So if I go into the negatives, you can see what it's doing with the decimals here. Sooner or later, the calculator is just going to give up. Like right now, this is saying literally move the decimal 28 spots to the left right here. And eventually, if you go for far enough, the calculator is going to be like, okay, fine, I give up. It's just 0. It's actually taking longer than I thought it would. Let's say I went to negative 1,000. Yeah, the calculator eventually, okay, fine. It's basically 0. So that's the idea of an exponential graph. And there's a lot of vocabulary and a lot of things I'll ask you for when you graph an exponential. The first thing I'm going to ask you for is going to be to determine whether the equation represents exponential growth or exponential decay. This graph is clearly, as you go to the right, next gets bigger, growing, so it represents exponential growth. If you have a number under your exponent that's bigger than 1, it's going to increase your answer every single time you go. So this is exponential growth. I will ask you to identify the asymptotes of the equation. So the asymptote is basically where your graph goes flat, and that occurs at the y value of 0 for this graph. I'll ask you for domain and range. The domain of this exponential, no matter what number you give me, I can plug it in and I can get you out a y. It's going to the left, and the arrow is going to keep on going this way forever. It's also going to keep going to the right as it goes up, so the domain is all real numbers. And then if you look at the range, the y's that my graph actually uses are all above my dashed asymptote right here. But it never actually will equal a 0, as I showed you guys. It's just going to be some tiny, tiny decimal. So the y's are just going to be greater than 0, not greater than or equal to, because it won't actually hit 0 in this case. Okay? The last thing I'm going to ask you for, and then we're going to move on to a new example, is the end behavior. We wrote this out with polynomials earlier in the year, but we haven't done with this in a bit. So as x approaches infinity and as x approaches negative infinity, we're going to say what's going on here. As x approaches infinity means as we go to the right side of the graph, and on the right, that arrow is pointing up to the sky. So we're going to have a positive infinity for f of x. As x approaches negative infinity, though, when we go to the left side of this graph and we continue right here, we're not going to infinity or negative infinity. We're actually leveling out at a number. So f of x actually is going to approach the number 0 on the left side of the graph. With polynomials, your only choice was infinity, negative infinity. With exponentials, you can have a number in there as well. So that was a flood of information right there. Let's go ahead and look at another example, and I think you guys will start to feel fine with these if you're not already. So my next equation is written right there in red, and we're going to start out by making a table. For our table, we're going to use the numbers -2 to +2. For today, all of our exponentials are going to use those same numbers. We're going to learn in our next lesson when we might want to mix those up. So I'm going to still go with -2 to +2 for right now. And then all I'm going to do is plug and chug. I'm going to plug in these numbers and I'm going to see what I get. Now I'm going to put those up there, but I want to caution you guys. When you have a problem like this, you are not allowed to multiply that 40 to the 1/2 and make it a 20. You would be breaking PEMDAS if you multiplied this because there is an exponent that applies only to the 1/2. So for example, if I wanted to do like a 0 plugged in, 40 times, I would be 1/2 to the 0 power. I have to do the exponent part first. 1/2 to the 0 is 1 times 40 gets me out a 40. You, of course, can just type this in the calculator as well. If you just type it in with a 0 in there, it'll tell you the answer. If I do a +1, that's going to be a 1/2 times 40, which is 20. If I plug in a 2, I'll get out a 10, and then a -1. So if I do a -1, that's going to flip this guy around, make him 2 times 40 is 80, and then this guy right here is going to be 160. If you haven't noticed, with exponential graphs, the pattern is, we talked about finite differences, like how much you add or subtract each time. When you have an exponential equation, you're actually multiplying or dividing every single time you go in your table. So there's a pattern involving multiplication or division. So I got to graph all these points right here. And this time I'm going to go by 20s, I think, just because it feels appropriate. So if I'm going to go by 20s for my equation, I would go ahead and graph my points, and I'm going to go ahead and do that here and throw them up for you guys. All right, those are going to be my dots that I've got graphed. And what I want to do again is think about just what would happen if I plugged in a really big number that was off my picture. Like, let's say I plugged in, I don't know, I won't even go that big. I'm just going to plug in a 10 for x, and I'm going to see what happens. Well, I would do 40 times 1/2 to the 10th power. I don't know what that is. 1/2 to the 10th power, some gross decimal. Let me see what I would get. I would type in 40 times 1/2 is 0.5 to the 10th power. and it's like 0.03. If I'm like, oh, actually, I wanted to do 100 right here for my exponents, that's what I really meant to do for x, it's still never going to actually equal 0. You're multiplying 40 times tiny decimal, and it will never dip below 0. So this time, when I graph my picture, my horizontal asymptotes is coming from the other, it's going in the other direction in the sense that we're going right to level out instead of left. But you can see what's happening here is we have a really steep side. This is hard to draw well. And then it goes flat like this. So I have a really steep portion to my graph and I have a really flat part as well. This would be my picture. So looking at this picture here, growth or decay, as we go right on this picture, my y's are getting smaller progressively. This is an example of exponential decay. I can tell it's decay just by looking at the equation because the number under my exponent is a fraction or a decimal less than 1. If you put a decimal less than 1 under your exponent right here, you're multiplying by a decimal, your answer is going to get smaller as you go. The HA, another way of writing horizontal asymptotes, the tail of my graph is still at y equals 0. Turns out that all exponentials we talk about today will always tail off at 0. We'll talk next time about when that can change. My domain is still going to be all real numbers. All real numbers. My range, the y's are still above 0. So it's still y is greater than 0. And then for my end behavior, as x approaches infinity, f of x, the y's on the right side approach 0. And then as we go to negative infinity is the left side, the y's approach positive infinity. All right, so I mentioned earlier, I was going to give you guys a definition for an exponential equation. It's just what we've been talking about. Exponents is the variable. The format you'll generally see these written in is a times b to the x. B is sometimes called the base. It's the number under your exponents. And when we do exponential equations, we specify that the number under the exponent has to be a positive number. So we put a positive number under here, not a negative. The why don't we allow a negative, is something I'll ask you guys about later as like a critical thinking challenge problem. But we only allow the number under the exponents to be a positive. Over here, the coefficients, that can be whatever you want. Positive, negative, it's cool either way. So we're going to do another example here, and this one I want you guys to try out for yourself. All right, so here's your next graph. Do the whole procedure here by yourself and get this all kind of taken care of here. I'm going to pause and come back just with everything worked out. So graph this equation, pause the video, and see what you can come up with here. All right, so here's the table of the values you guys should get, and I filled out a few of the pieces, but I wanted to talk about other ones. For today, again, the asymptotes of the exponential will always occur at 0. It always levels out at 0. We will talk in 5-2 about when that's not the case, but for tonight's homework, you assume the asymptote is at 0. So if you look at the points, you can kind of see which way the points are bending. I chose to go by 5s here. If you went by something else like 10s or 2s or whatever, it doesn't matter as long as you have it labeled. But you can see the points sort of are bending and going flat in this direction. So my flat side, my tail is going to go to the left right here. I'm going to hit all my nice dots. And then I'm going to go really steep on this bottom part over here. So this is going to be my picture. So growth or decay is a weird thing for this sort of graph right here. This graph is actually considered exponential growth. It's just growth in the negative direction. If this graph had a positive number right here, if this was a positive 6, it would look like this. Because what that negative does, if you guys remember from our square root lessons, I don't know why it's deleting it right there, but what it does is it flips it over the x-axis and makes it go upside down. So picture like we had this guy right here. That would be the original picture, but that negative flips it and makes it go upside down right here. The best way to decide growth and decay is to go by the number under the exponent. If you see something that's bigger than 1, that's going to make your answer grow, this time just in the negative direction. If you see a decimal here, less than 1, that's going to be a situation where you would choose decay. The range on my blue graph right here, the y's are all under 0. The y's are less than 0 for my picture right here. And then if I set up my end behavior, as x approaches infinity, f of x approaches. So when we go to the right, the y's go to negative infinity. And then when we go to the left on this graph, the y's approach 0. So we're going to do one more example, but not all the way through. This is going to be a faster one right here. Because what I'm going to do, I'm not even going to worry about all this stuff. So we're not going to bother with this. What I want to do instead is I want to sketch a quick picture. The word sketch in math means don't spend a lot of time on it. Just draw like a quick thing. And if we look at this equation right here, I see that I have a decimal underneath. The decimal is going to make it decay. So if we look, this would be what growth looks like. This would be what decay looks like. So we're looking at this kind of picture right here. But it's also got a negative. So what that's going to do is it's going to flip it over the x-axis. We are actually going to be looking at this kind of a picture right here. The tail is still going to be at 0, because we haven't learned otherwise yet. And I don't know exactly where it goes flat and stuff. But just to give you guys a basic sense of what's going on, I would expect to see this sort of a picture. And this would represent exponential decay. So we've learned what an exponential looks like, but we have more to learn in terms of like, how do you know what x's to choose? For today, just always go -2 to +2, but we're going to learn more detailed stuff that'll make this make more sense in our next lesson.